Alright, so the goal of this was to look at COVID-19 cases and to be able to determine if, based off the time series graph, if the next day will either increase or decrease in the number of positives. So that's what it's talking about here is, emphasis on flattening the curve. So we need to see if it's going up or down. So the way I did this, I first did feature selection using ARIMA. And this kind of told me the viewing window, how many days to look at, and if we should look at either the change in the number of cases or if we should look at the absolute value, the number of cases. After I did feature selection with ARIMA, then I tested multiple classification machine learning algorithms from scikit-learn to see which would be the most robust. So the first thing here in the code is a bunch of stuff we got to import, so we can skip over that. The next thing here is different parameters that we can optimize. The first is the number of missing days in the time series that will allow the program to accept data. So if there's big gaps in the data, the program's just going to reject it and not use it because it's trash. I set that to 2. This can be changed. The next is the minimum number of days required to accept data. So I set that to 20 days. And the maximum number of positive cases, I set this to 20. Because countries that are kind of relatively new to this, they skew the results, like if they only have 1 positive. So I did this to threshold that. And the other are either just to rerun results or to read old results for different things. So the first step I did is just reading in the data. And I took it from this website right here. I found the European CDC had more available data. So I ran with that one. So this was just some mungling that needed to be done. And here's the raw data for each country. So you can see here's the China, the big spike and going down. And if we look at this, we can see not only is it jagged, but there's also gaps. Like if you look right here, there's a skip in this Brazil one right here. There's a skip right here because it's missing days. And you can see more skips as we scroll down a little bit more. Finland in this next one has a few skips. Russia has some big skips, and Iraq has some big skips. So that's why that was important to put that threshold earlier on how many days can be missing before we accept data. Alright, so the next step was to do feature selection, and that was using ARIMA. And this was doing this auto correlation. So it looks at the number of lags that are correlated to the current value. So it means, looking at, say, day 20 after the outbreak, how many previous days should I look at for correlation? So for this example, it shows for China, it shows up to about 10 lags has a high correlation, and then it kind of drops off. So I did this for all the countries. I'll skip through them. You can see there's a lot. It sounded like, looking at all these, it looked like between 1 to 2 tens or 1 to 10 lags are correlated. Some countries benefit from more, but most are around 5 lags. So ARIMA is pretty good to get a baseline of how many lags and derivatives should be used. So derivative would look at the change from one day to the next, as opposed to just looking at what the exact value is next. And then the moving average, what should be the window. So here is the loop I set up for ARIMA. Highlighting these 3 for loops right here. These kind of iterate through the number of days. This is the number of lags. The derivative, so it's either 0 or 1. So this should actually be 2 here. I had it parallelized to make it run faster, so 1 tested 0 derivative, 1 tested 1. So that's why it's like that. So this is either, if it's a 0, it's looking at the absolute value of the current day. And if it's 1, it's looking at how many cases has changed from the next day. Lag is the number of previous data points to look at, whereas remember this number of days is looking at what's in my window for the previous lag. So if n days is equal to 5, that means it's setting a moving sum of 5 every 5 days. And then lag is looking at the n number of those windows before it. So this is just looping through and testing them all. And then the results are down here. There's a lot, we don't have to look at them. I'll just show the ones that did the best. But I tabulated the lags, derivatives, so either 0 or 1. Days, so this is the size of the window. 0, 1, 2, 3, 4, 5, 6, 7. I did as much as a week. And then here's the root mean squared error percent of the predictions, the root mean squared error, how many data points converged. Not all the data points converged in ARIMA, and how long it took to do it. So after looking at this table, I put the source code in the PDF in the zip if you want to look at this more details. I found 3 possible models. The first one uses 12 lags, derivative in the 6-day moving window. The second one was just 1 lag, 1 derivative, and 0. So let's just look at the previous day. That's it. And try to predict from that. The last one was a 4 lag and 2-day moving window with 0 derivative. So these are the 3 models I wanted to test. So now that we have these, we can look at machine learning. So in order to prepare the data for machine learning, I took the moving sum of these 3 models. So the moving sum of model A looked at the previous 6 days. B, there was no moving window, it just took the current day. And C was looking at a moving window of 2. So that's what created these 3 data A, data B, and data C. So if you look at it, data A is a moving window of 6 days. Data B is just all the data because it's just looking at the previous day. And data C is a moving window of 2 days. So I went ahead and I went through and split these into training and testing sets. And I split it 10% into the testing and 90% into the training. And that's what's happening here. That's what's right. This if random is greater than test split, then I put it in the test. Otherwise, I put it in the train. So test split is equal to 0.1. So this is putting 10% into the test and 90% into the train, roughly. I'm just writing it as a pickle for easy access later. So here are the graphs for the 8-day moving sum. You can look; they look a lot smoother than earlier. China jumps up and down. Germany, Italy, Spain, USA are all shooting up. When we look at the moving windows for these other countries here, again, if you want to look at these in more details, they're in the zip. And see South Korea is another one that went down. All their ones are going up. Looks like Iran's starting to level up. And here's some more down here. So they look a lot more smooth. So this is probably a lot better for training. So now I wanted to look at, I used cross-validation. Should we be using model A, B, or C? And if you remember, here are the models up here. Here's model A, B, and C. These are the 3 different ones we're testing. So I used 10-fold cross-validation. Cross-validate for model selection. And I was testing a few different machine learning algorithms to detect if the next day will go up in cases or down in cases. And here they are right here. Decision tree, naive Bayes, random forest, extra trees, support vector machine used for classification, k nearest neighbors, and a MLP, which is a neural net. Alright, so I went ahead and I tested each of these models. So that's what's going on here. Model A, here's all the average classification accuracy, and I plotted them below. So we're going to skip ahead and look at the plot. So here's the cross-validation results for Model A. If you see, there's a bunch of green dashes. Each green dash is one of 100 random runs of cross-validation. So you can see ML stands for multi-layer perceptron. It went up to 85, but can be pretty low. Decision DT, that's decision tree. That's between 80 and 90. RF, that's random forest. It's around 85. And ET is extra trees, around 85. Naive Bayes drop below 75, and support vector machine hover around 85. K nearest neighbors below 75. This is for Model A. Model B did a lot worse, and Model C did even worse. So we can clearly see that Model A was the correct one to do, because all these are above. So I chose to go with Model A. And the next thing was to do is check what machine learning algorithm. And looking at this, looks like support vector machine is the best. It did right around as good as these 3 here. These 3 potentially could get higher, but they come at the risk of more overfit because they're way more dependent on random seed. So I went for support vector machines since it's not dependent on random seeds at all. So the next step then is to optimize the support vector machine, and that's what I did here. I tested a bunch of different parameters. The kernel, the regularization, the tolerance, shrinking, gamma, coefficient. This only depends if you're doing a poly or sigmoid. Coefficient matters. Anyways, I did a bunch and just used cross-validation on the training set, and the highest accuracy was 85%. And here's all the different parameters that got it. I'm going to sum it up right here though. Kernel RBF is the best. Gamma auto is also the best, and a regularization of between 10 to 10,000 are all good, doesn't matter. The coef, shrinking, and tolerance makes no difference. So the final model I use is right here. An RBF kernel, gamma auto, regularization of 10, and outputting the probability. So the final results here, trained on the entire train set, and then I tested on the test set that's been left out up until this point, and the final accuracy was 83%, which is pretty close also to the cross-validation accuracy we're getting of 85%. So it shows it's not overfitting. That's it. So hopefully this model maybe could be used for something to predict if tomorrow the predictions will go up or down. More future work would be to predict more than just the next day, and then also predict how many cases it will go up or down. But that's a little out of scope of this. That's it. Thanks for watching.